Assalamualaikum warahmatullahi wabarakatuh, and a very good evening. Happy to my lecture, Dr. Sabira Khatun. I am Anwar bin Mohammed with matrix number of EA18122 BEE3413. So now I will be presenting about my lab. I decided to do a double sideband suppressed carrier Dsbsc. So what does double sideband suppressed carrier? So double sideband suppressed carrier is just similar to double sideband full carrier, but in this case it has no carrier signal because we want to overcome the power waste in the carrier signal. That means when we calculate the the efficiency, as we know for the Dsbsc, the power total is equals to power of sideband. So if the total power equals to sideband, so that means for the efficiency calculation, the power sideband power will divide by power total. So it means that power sideband will divide by power sideband. It means the efficiency is always 100%. So for the carrier suppressed carrier, it means that when uh, we program the code for in on MATLAB, we get the suppressed carrier at this point. As we as you can see here, it intercepted from the absolute value of upper one and the negative absolute value from the lower one. So the interception indicates the phase transition of the suppressed carrier. As we can see here, at this point and this point, it is the sideband carrier. No, I mean the sideband wave, which means there is no carrier. The carrier is already suppressed. By comparing to the DSBFC, the carrier exists. There's no intersection of the absolute value here. So when we plot the spectrum, I will show you after this. The carrier signal spectrum will not appear as it's already suppressed by the system or equation, and we can see the bandwidth is still the same, it's 2 FM, and the waveform of the spectrum form is only the spectrum of sideband spectrum, or we can say the double sideband spectrum. So from the theory, as we can see, double SC, we don't need this equation. We only need this. This what we found out in the spectrum. In spectrum analysis, we can see that M is C divided by 2. So this is MC divided by 2, the amplitude. And of course, the frequency of the carrier signal is needed here. As you can see, this is the the Dsbsc equation. As we remove this equation, EC sine omega c t. Meanwhile, the power calculation is the total sideband is the power of total sideband, which is em square divided by 4r. I will show you in the MATLAB program later by GI. So after we did the modulation, we will go through to the demodulation. For the demodulation, let's say that we have the incoming Dsbsc here. We will multiply by the carrier carrier wave. Be noted that the frequency must be the same as the carrier wave. If we set the carrier frequency of 50 hertz, so the incoming carrier equation must be also 50 hertz. So in the MATLAB, we will multiply the SPLC with the carrier wave of cos omega omega ct, and it will form the equation of ET and pass through the low pass filter. As we can see here, the ET is the product of MT and cos omega ct squared because of the same identical variable here. So it will form the equation of 1 over 2 mt plus mt cos 2 omega ct. So which means 2 fm. 2 fc. I'm sorry. So as you can see here, this is the double sideband suppressed carrier spectrum. We can see this is upper sideband, this is lower sideband, and after multiplied by the carrier wave of cos omega ct, the the um the carrier wave is double here, 2 omega c. So for the MATLAB GI, I designed my GI figure here with 3 panels of input, push button, and result. This result and push button depend on the input I insert later. Okay, so this is the most important push button, where the modulate will control the axis of 1, 2, 3, and 5, while demodulate will control the axis of 6, 7, 8, and 9. This is axis 9 here. And when I click the modulate, it will display the waveform and also the result of bandwidth and total power. So when I click the modulate, it will display the waveform on axis 6, 7, 8, and 9. This is what I designed earlier. And for my coding is a bit long. I think it's a bit long, where I just need this kind of functions for the input purpose, where value 1 equals to str2 num get handles fm string. So fm means fm here, that name of fm. So when I insert the value of baseband frequency, for example 1 hertz, it will detect or get the input of 1 hertz and will be stored into the value 1. So after I get my equation of value 1 and value 3 of EM, I can plot my uh, modulating signal, and as well as the carrier wave signal, as I need the value 4 and value 2 here. Value 2 is FC, value 4 is EC. Okay. After that, I get the Dsbsc signal, and then I calculate the bandwidth, I calculate the total power, and I form the spectrum of the Dsbsc. As you can see, axis handles axis 5. So I want the waveform appear on the axis 5. This is very important for GI purpose. As you can see here, SS2, SS1, SS3. And then I've create another push button of apps for the absolute value. I mean, this apps is the this here absolute value. Okay, so I need to declare once again the value 1, 2, 3, and 4, and I get the value m, and also the negative apps, which is here negative apps. I just create this push button to highlight the the suppressed carrier, why how the carrier is suppressed. So I just it's 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 up to the creator if he wants to create the apps or negative apps push button. It's not necessary. So the clear button, I will come back to you with the clear bar push button. So I will go to the demodulate push button is here. Demodulate here with tag name, and once again I declare the val1, val2, val3, val4, and I declare the sampling frequency and the time domain. So as we can get the val1, val2, val3, val4, if we insert the value of fm, fc, em, ec, they will be stored in the val1, val2, val3, val4 respectively. So I can get the value of m, the carrier frequency, and the Dsbsc equation. This is for product modulator output. The product modulator output is here. This is my product modulator output here. The carrier wave will multiply by the Dsbsc equation, and then I plot the product modulator output on the SS6 with the variable of z, and then I found the spectrum of 8 on the axis 7. This is the Fourier fast transform. This is for the spectrum of spectrum formation. And then what I need is the function of butter. This is a Butterworth filter design. I need the variable num or number or and the denominator. It's not a number, it's numerator and denominator. And the 5 here is filter order, and low means low pass. I can write high, it is for high pass. I can write stop for stop, for band stop. So I tried here low because we want to experiment the low pass filter. So I declare the variable of REC, which means a recovered signal, and then I use the function of filter for the low filter purpose, and then I plot the low filter or the recovered signal on axis 8, and finally I get the spectrum or low pass filter output and on the axis 9. So on top of that, I did the simulating for the I I create a simulated model for the Dsbsc. This is without the low pass filter or the recovered signal, or without the demodulation. Okay, now let's run the code. This is what we call val1, val2, val3, val4, and val5. So I start the value of val1 of 4 hertz. As this example, the val2 of 50 hertz, the val3 of let's say 3 volt, and val4 of 5 volt. And to make it easier, I just insert the value of resistance of 1 ohm. And now I will click the modulate button and it will display axis 1, 2, 3, and 5. Okay, so this is my baseband signal of 4 Hz and the carrier signal of 50 Hz, and then this is my DSP signal of 8 volt of maximum Vmax, and of course the Vmin is 0. So I I want to check if it's the suppressed carrier or not. So I just click on the absolute push button and the negative absolute. So it is suppressed carrier here. As you can see, the interception or the phase transition here, the carrier is suppressed, and you can see here because of the GI, I cannot zoom in to show you the value of the frequency here. It means this is 54 and 46. Am I right? Yes. And the FT point here. So we are done on this spectrum of the message signal or the DSP signal. And now I will demodulate the signal to recover back to get the low pass filter signal. So this is my product modulator. Product modulator is here. Product modulator after multiplied by the carrier wave of omega c, and then I get the spectrum, which why it is 100 here. Why it is 100? Because as I explained before, this is 2 omega c, which means 2 fc. When 2 fc, as we can see that fc is 50 hertz, so 2 fc is 100. So it will be 104 and 96 here. Okay, and this is my recovered signal. And the low pass signal is because of time domain of 500, absolute frequency domain of 500 until negative 500. So we can actually zoom in the value of the low pass filter frequency here. As you can see, this is 4, this is negative 4. As I click the clear button here, it will all disappear and this all was set to 0. So we can play again and again and again. So let's try new value, 10 off, and then 100, and let's say 8. I put here 10 and 10 ohm. So let's modulate. So this is my modulation of analog signal in the Dsbsc, and I want to check if it's DSP signals or not. So I click the absolute value and then I click the negative absolute. Yes, it is indeed DSPFC signal, and this is actually the spectrum. As you can see here, it is wider than before because we set the carrier frequency of 100 and the modulating frequency of 10 Hertz, and this is 110 and 90. Okay, so I demodulate now. As you can see here, it's beautiful. So why 200? Because as we can see 2FC, 2FC, which means 2 times 100, 200. So 210 here, this is 190. As you can see, there is no carrier spectrum. This carrier spectrum is suppressed, and we get back we recover back the signal after through the low pass filter, and we can see here the spectrum of low pass filter signal of 10 hertz. So now I will show you the simulating model, and I will run it. Okay, 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 okay. This is my spectrum message signal. So as we can see, I insert the value. I insert the value of frequency. Frequencies. I insert the value of 4 hertz for the message signal. So let's zoom in. Is it 4 signal? Is it 4? This is indeed 4. I'm sorry. I think I insert the value of sine wave of 5 hertz. I'm sorry. This is not 4. This is 5 hertz. 5 hertz. So use my message signal, and then I'll show you the SBSC spectrum. Yes, it is same as before. Let's compare the result. Spectrum analyzer and the spectrum of message signal. This is actually the SP signal. So I will zoom in. This is before, as before, I insert the value of 4 hertz of FM and 50 hertz of FC. So this is actually 55 hertz and 45 hertz. So there is no carrier spectrum here. This is already suppressed. So it is proof that by using the equation, I get the suppressed carrier with the double sideband. So I think that's all for my presentation of the SBSC. This is my GI figure, and I would thank to my lecturer for sharing her knowledge to me when I texting her. I wish you a very good day, and thank you very much.